student. Now today we'll continue from the last lecture of semiconductor laser. We have the last lecture we have done about the lasing condition and the gain in the semiconductor laser. So from there again we'll move ahead and we'll talk about optical activity. We are discussing in short actually. So optical activity, basically for lasing to take place, optical activity is required. Now in a semiconductor laser, the Fabry perot, optical cavity is found by cleaving both sides of the diode. The cleaved edges, being optically flat to near perfection, serve as the mirror of the cavity because of the large refractive index difference between the semiconductor material and air. Thus, external mirrors are not needed in a diode laser. The reflectance at the boundary of the air, boundary of semiconductor air is given by R equal to mu2 minus mu1 by mu2 plus mu1 whole square. So here mu1 and mu2 are the refractive index of the semiconductor and air respectively. Taking you just take the value of this mu2 equal to, say for example, mu2, if you take mu2 is equal to 3.6 and mu1 is equal to 1, then you'll get R is equal to 0.3t. You can just do the calculation. It means that above 32% of incident light gets reflected. From here you can conclude that 32% of the incident light gets reflected into the medium, providing enough feedback for the lasing action. So the initial light output occurs due to spontaneous emission, transition of carriers between the two energy bands, and it is selectively amplified as the light travels in the cavity between the end mirror and is fed back. During the round trip, there is an amplification as well as absorption in the light intensity. Lasing occurs when the gain provided by the medium overcomes the losses in the cavity for a round trip. Now, next thing is like threshold condition. Threshold condition for lasing. Now we consider a PN junction diode where the laser cavity is of length L, capital L, and has a sides of mirror polish. Now we will consider that the reflectivities of the two ends be R1 and R2 respectively. We denote I naught. I naught, intensity of the light. Intensity of the light at the beginning of the round trip. And here we also assume alpha. What is an alpha? Alpha is the absorption coefficient. We consider alpha as the absorption coefficient within the medium. Then the intensity of radiation after a round trip. So I is equal to I naught R1 R2 into e to the power 2 into gamma minus alpha into L. So it will be given by this much. Here the diode will start functioning as a laser if I is greater than equal to I naught. It requires that gamma should be greater than alpha. So at the threshold, when the round trip gain exactly equals the losses, then I is equal to I naught. Therefore we can write R1 R2 e to the power 2. That will give the threshold value gamma th minus alpha into L will be equal to 1. I naught and I naught will get cancelled out. So here gamma th is the threshold gain. So applying log on both sides, we'll get gamma th equal to alpha plus 1 by 2L ln 1 by R1 R2. So after a few oscillation, laser action reaches a steady state and the gain maintains at a steady state value equal to gamma threshold. Then there is again a short topic, say threshold population inversion. Okay, so the threshold population inversion can be expressed as n2 minus n1 th equal to 8 pi mu naught square gamma th, okay, tau spontaneous mu square by c square g as a function of m. Or this could be written as nth. We already have discussed this whole thing in the previous lectures. 8 pi naught square gamma th tau s p del nu into mu square by c square. The above equation contain terms that are either physical constant or parameters that can be determined for a real laser. Then we have threshold current density. Okay, so the population inversion occurs in semiconductor over an active thickness d, say for example. However, the thickness over which the optical mode extends is d subscript m, which is basically usually larger than d. So the threshold density of the injected carrier can be written from equation. We'll use this previous equation, can be written as mth equal to dm by d, okay, then 8 pi mu naught square th tau speed mu square divided by c square. So this is the threshold density of the injected carriers. Okay, so you need to know this thing. Then further we have already discussed earlier that there is a relation which we have discussed previously. That is the equation was like it's n by tau sp is equal to j by ed, which we have already discussed in the previous lecture. So we'll use this particular one and apply for the threshold condition again. So jth will be equal to nth into e into d by tau. Okay, so using the last equation and this particular equation, we'll get jth. Okay, we'll substitute the value of nth from the previous equation. E dm by tau, okay, 8 pi naught square gamma th by c square. Okay, now we'll substitute the value of gamma th, which we have already have the gain. Okay, so the threshold gain, you can substitute the value of this threshold gain y gamma th over here to get j th equal to 8 pi mu naught square mu square e dm tau sp del nu by c tau c square in fact, and then with a bracket alpha plus 1 by 2l ln 1 by r1 r2. Okay, so from the equation it is seen that the threshold current density jth does not depend on the thickness of the active layer d. Okay, as we assumed before. On the other hand, it is directly proportional to dm, d subscript m, which we can see from here. Now, the power output. Okay, further power output. What will be the power output? So these are all the generalized equation for the laser, semiconductor laser. So the power output, the optical power output, in fact, into model volume due to current I, to the current I, which is greater than obviously ITH, can be written as P subscript E is equal to I minus ITH by E into N subscript I H nu. Here, in fact, eta you can take this to be. Here, eta subscript I, it denotes the internal quantum efficiency of the semiconductor. Okay, part of this power is dissipated into the cavity while overcoming the cavity losses, and a fraction of P subscript E is coupled out through the end facet as useful light output. So the output power of the laser can be written as, this could be written as PO, output power, that is I minus ITH by E, and eta I H nu, and then it could be written as 1 by 2L into ln 1 by R1 R2, this whole thing divided by alpha plus 1 by 12 ln 1 by R1 R2. Okay, now we will talk about the efficiency. As far as efficiency is concerned, we can say the efficiency of semiconductor laser. So efficiency, like it is given by overall efficiency of the laser in converting electrical power into output optical power, may be written or may be defined as eta equal to P naught by Vi. So eta could be written as P naught. You know the value of P naught. We'll just find out the value of P naught in the last topic. So I minus I TH by I, okay, into n eta I H nu by E V ln 1 by R1 R2, okay, whole divided by 2 alpha L plus ln 1 by R1 R2. So this is the some of the terms associated with semiconductor laser before starting or before conducting actual study of the semiconductor laser. So in the next topic or in the next lecture, we'll start discussing about the basic laser structure, diode laser operation, and with that we'll finish off our this particular topic, semiconductor laser. Until then, thank you.